Welcome. In this video, I'm going to take you through the design and implementation of my own dynamic string type in C. This isn't a beginner C tutorial. We'll focus on the functionality, the API, and the design decisions that make it work. You'll see how the data types and functions fit together, why certain return values and types were chosen, and how I test everything. Before we dive into the library itself, I like to quickly make sure my environment's behaving. A simple hello world does the job, compile, run, done. Now let's look at the types we'll rely on throughout the code. These short aliases are mostly self-explanatory. They give me fixed-width integers and floating-point types, which keeps the code portable and consistent across platforms. The more interesting part is the error macros at the bottom. They wrap existing errno values into a custom naming scheme. This way I get clearer, less cryptic error codes in my API, and I can add detailed explanations or introduce finer-grained definitions later without breaking the interface. Errno by itself can be pretty vague, so wrapping it gives me both consistency and room to grow. Now let's move on to the heart of the library, the dynamic string type. This header starts with a few standard includes and my own data types, each so we can use the fixed-width types we just defined. Nothing exotic here. Here's the actual string structure. The data pointer points to the dynamically allocated buffer where the string characters lie. Size tlen tracks the current length of the string, that's the number of characters, not counting the null terminator. This makes operations like append or slice much faster because we don't have to call strlen every time. Size tcap stores the total allocated capacity of the buffer. It's usually larger than len, which allows us to grow the string without reallocating on every single append. Finally, U32 magic is a small but important detail. It's a magic number we assign at initialization. When we later pass around a din_str pointer, we can quickly check that it was actually initialized by our API and we don't have a struct with leftover garbage memory. That's a cheap guardrail often used in plain C. With the struct defined, the next piece of the API is the lifetime functions, everything you need to create, reset, and free the dynamic string. There are several initialization functions because not every use case is the same. dsinit sets up an empty string with a default capacity, quick and easy. dsinit lets you specify the initial size yourself if you know roughly how much space you'll need. That can save reallocations for large strings. ds from cstr takes an existing C string and initializes the dynamic string from it, automatically allocating enough memory to hold the content. And ds from file goes a step further. It reads an entire file into the buffer. All four calls follow the same pattern and the same return codes, so the API stays predictable. To clean up, ds_free releases the memory and resets the struct to an uninitialized state. If you only want to reuse the buffer without freeing it, dsclear does just that. It resets the length to 0 but keeps the capacity, which is useful for repeated builds. All of these functions return an i32 status code instead of, say, a pointer. That's deliberate. It gives you a consistent way to check success or failure with the error macros we defined earlier, and avoids mixing allocation logic with return values. Together, these functions define the lifetime of a din_str object, initialize in one of several ways, operate on it, and then either clear or free it. Inside the implementation file, we pull in the standard headers plus our own definitions. I define a magic constant here. This is the value we'll store in the struct's magic field, so we can later verify that a din_str has actually been initialized by our API. Init is the simplest initializer. The first thing it does is check if this string is already initialized by comparing the magic number. If so, it returns already initialized, otherwise it allocates a default capacity, 4096 bytes here, and sets up an empty string with a null terminator, 0 length, and the magic number. The return value success signals everything went fine. The init is the same idea, but lets the caller specify an initial size. I even add a small buffer on top to cut down on reallocations during growth. Everything else is the same: allocate, 0 length, null terminate, set magic, return success, or an error code. The s from cstr starts from an existing C string. It checks for an existing initialization and for a null text pointer. It then allocates enough capacity for the incoming data by calling dsinit internally, and finally appends the content using a yet-to-be-defined append function. The append functions will be defined shortly, but I use it already as this keeps the API consistent and avoids duplicating code. Finally, ds from file does the same but with a file handle. It figures out the file size, allocates enough capacity in one shot, and reads the entire file directly into the buffer. If anything goes wrong, it cleans up and returns an appropriate error code. Almost every following function in this library needs to check whether the string is actually valid and initialized before doing anything. Instead of rewriting the same checks everywhere, I'm going to create a single macro for it. This validate macro does three main things. It checks that the pointer itself isn't null, it verifies our magic number, and it makes sure the buffer and capacity look sane. If any of those checks fail, it immediately returns an error code. Using a macro here keeps the implementation of each function short and consistent, and if I ever want to change the validation rules, I only have to do it in one place. With validate in place, the ds-free function becomes simple. Free the buffer, reset the fields to 0, and clear the magic number so the struct goes back to an uninitialized state. Return success to signal everything's fine. ds-clear uses the same validation but doesn't free memory. It just resets the length to 0 and writes a null terminator. That lets you reuse the same buffer for repeated operations without paying for new allocations each time. With initialization, freeing, and clearing handled, we've defined the full lifetime cycle of a dynamic string. From here, the other API functions can build on this solid base. With lifetime management done, the next step is basic string operations, appending and removing content. All functions follow the same design. They take a pointer to the string as the first argument, they validate that it's usable, and they return an integer status code. That consistency makes the API predictable. ds-append str takes a null-terminated C string and adds it to the end. This is the workhorse for combining strings in the library. For single characters, there's ds-append char. It's lighter than wrapping a character into a one-character C string, and more efficient if you're building strings character by character. ds-append fmt is a convenience function. It works like print, letting you format into the dynamic string directly. It's especially useful for building structured text or logs without juggling temporary buffers. On the other side, we have functions that modify existing content. ds-remove-range deletes a slice of the string, given a start position and length. That lets you surgically remove part of a string without rebuilding it from scratch. ds-insert-str does the opposite. It inserts a C string at a specific position, shifting the rest of the content as needed. That's handy for building or editing text dynamically. ds-append str, I get the length of the text and call a helper ds-ensure to make sure there's enough capacity left in the buffer. You'll see that function later. Once the space is guaranteed, it's just a mempy into the right offset, bump the length, add a null terminator, and return success. No surprises, but very fast. ds-append char is the same idea, but for a single character. It still calls ds-ensure with a size of 1, writes the character directly, updates the length and terminator. ds-append fmt is a little more involved. I'm using vsnprint to do a 2-pass size calculation. First, I copy the var list and call vsnprint with a null buffer to find out exactly how many bytes the formatted output would take. If that comes back negative, it's a format error. If the size is positive, I again call ds-ensure to make sure we have that much space. And then do the real vsnprint directly into our buffer at the current end. Finally, I bump the length by the number of bytes written. This approach avoids allocating a temporary buffer and keeps everything in one place. For ds-remove-range, I just check that the range is valid, and then use memove to shift everything after the removed slice down over it, including the null terminator. Memove handles overlapping regions safely, so it's perfect here. ds-insert-str is the inverse. After validation and capacity checks, I use memove to push the existing content up to make room, then mempy the new string into the gap and adjust the length. By building on validate and ds-ensure, all these operations stay short and consistent. You don't see manual reallocations sprinkled everywhere. The helper functions and macros take care of it. With appending and removal done, the next piece is read-only operations, comparing and searching. For comparisons, I keep it simple. ds-compare compares two dynamic strings, and ds-compare cstr compares a dynamic string to a plain C string. Both return 0 when equal, negative if the first is less, and positive if the first is greater, just like strcmp. That makes them drop and intuitive for anyone used to C's standard library. For searches, I split things by what you're looking for. ds-find char scans forward from a starting position for the first occurrence of a character, returning its index or -1 if not found. That starting position parameter lets you skip over a section without slicing or creating temporaries. ds-find str is the same pattern for substrings, built on str. And I have ds-find last char and ds-find last str, which search backwards for the last occurrence. The substring version explicitly checks lengths and runs a backwards loop with strncmp, so it's predictable and safe even when the substring is longer than the source. Here's the implementation of the compare and search functions. Compare functions are deliberately thin wrappers over strcmp. Inside ds-compare, I validate both strings and just call strcmp on their internal buffers. Same for ds-compare cstr, except I also check for null pointer on the C string. This keeps performance high and behavior identical to the C standard library, so users already know what to expect from the return values. Search functions are a little more interesting. For ds, find char, I call memker starting at the offset you pass in. That avoids re-implementing a scan and lets me search only the remaining slice of the string. If nothing's found, I return -1. That's why these return s-size t instead of an unsigned size type. ds find str uses str in exactly the same way for substrings, again starting at the given offset. The two last occurrence functions don't have a standard library helper, so I explicitly loop backwards. ds find last char just scans from the end towards 0 until it finds a match. ds find last str is the most manual. I pre-compute the substring length, bail out early if it's 0 or longer than the main string, and then slide backwards one position at a time using strncmp to check for match. It's not as fast as a dedicated search algorithm, but it's predictable, safe, and easy to understand. Next up are the substring and transformation functions. The two substring functions exist because in practice you often need to extract part of a string into a brand new dynamic string. ds substring gives you full control. You specify both a start index and a length, and it fills a din str you pass in. That way you decide where that new string lives and how you manage its lifetime. ds substring from is just a convenience wrapper for the common case of from here to the end. It keeps the API readable and prevents you from having to compute the length yourself every time. Both functions return an error code instead of pointer, which keeps error handling consistent with the rest of the library. Then we have the transformation functions. These all modify the string in place. ds to lowercase and ds to uppercase do exactly what you expect, but only for ASCII letters. This makes them fast and predictable without pulling in locale-specific behavior. ds reverse is another in-place operation, swapping characters from both ends until the string is reversed. Having these as dedicated functions means you don't have to copy data around manually or worry about temporary buffers. You just call them and get the effect directly on your dynamic string. Now that we've defined the prototypes, let's implement them. Starting with ds substring. After the usual validation, we clamp the requested length so we don't read past the end of the source string. Then we initialize the result dynamic string with exactly enough capacity using ds init. This is important. We're returning a new independent string here, not just a view into the original. Finally, we copy the requested slice and set the null terminator. That guarantees the caller can free or modify the substring without touching the source. ds substring from is just a thin wrapper. It computes the remaining length from the starting position and calls ds substring. This keeps all the allocation and copy logic in one place, which means less code to maintain and fewer bugs. The transformation functions work in place. In ds to lowercase and ds to uppercase, I'm deliberately not using to lower or to upper from ctype.h. Those are locale dependent and often slower. Here I'm just checking the ASCII ranges and adjusting the character code. That keeps behavior predictable and fast for typical text. ds reverse uses the standard in-place swap trick. It loops from both ends toward the center, swapping characters until the string is reversed. This is O of n time, 0 allocations, and it's immediately obvious what's happening when you debug. Next up, I'm adding trimming and replacement functions. The three trim functions are a common pattern you see in string libraries. ds trim handles both ends at once, which is the usual case, but I split it into ds trim start and ds trim end as well. That lets me chain or mix operations without extra copying, for example, trimming just the start when parsing input lines. This is why all three share the same signature and return code. They are predictable and composable. Replacement API mirrors that thinking. ds replace handles the common case, replacing every occurrence of a substring with another substring. But sometimes you only want to surgically replace a known range. That's what ds replace range is for. It works directly with positions and lengths so you can control exactly which part is affected. And finally, ds replace char is the simplest and fastest path for single character substitutions, which are very common when sanitizing text. Let's implement them. The main ds trim is just a convenience wrapper. It calls ds trim start first, then ds trim end. That way I don't duplicate trimming logic in two places and the user still gets a one-call option. Inside ds trim start, I count how many whitespace characters we have at the beginning. Once I know the count, I shift the remaining content down with memove. That's important. Memove safely handles overlapping regions, unlike mempy. Then I just adjust the string's length. ds trim end works in reverse. It walks backward from the end, counting trailing whitespace, then shortens len and renull terminates the buffer. No extra allocation, no copying unless necessary. For ds replace, the logic is a bit more involved. Instead of trying to modify in place, which would be messy if the replacement text is longer or shorter than the match, I build a brand new dynamic string piece by piece. I append the text before each match, then the replacement, and keep going until there are no more matches. At the end, I swap the old content with the new one. This approach is more expensive but clean and avoids subtle off-by-one errors. ds replace range is the more surgical version of replace. Instead of working with substring matches, it works with exact positions and lengths. The first thing it does is validate the input and clamp the removal length, so even if you ask to remove more than what's left in the string, it won't step out of bounds. Then comes the tricky part, making sure we have enough room for the replacement, since the new string might be longer than what we're removing. I calculate the new total length, and if the current capacity isn't large enough, I grow the buffer. The growth strategy here as well is to keep doubling until it fits, which keeps reallocations relatively rare and efficient. Using realloc also has the advantage that it can reuse the same block if possible, but still gives us a bigger buffer when needed. Once the buffer is big enough, I deal with the tail, if the new string is longer or shorter than the old one. The tail has to be shifted to its new position. After making space, I copy the replacement directly into position, update the length, and the operation is done. Finally, ds replace char is the simplest. It's just a single loop scanning for the old character and swapping it for the new one in place. Fast, predictable, and doesn't allocate. Now at the last section of the dynamic string API, the conversion and utility functions. Most of these are small helpers, but they round out the library and make it much nicer to use. The two conversion functions, ds to int and ds to double, are for when you need to treat the contents of a dynamic string as a number. They take a pointer to store the converted value and return an error code if parsing fails. This is more explicit and safer than just returning the number directly, because it forces you to handle error cases like invalid text or overflow. Utility functions are mostly about inspection. ds starts with, ds ends with, and ds contains cover the common patterns of checking prefixes, suffixes, or the existence of a substring. They all return simple booleans so you can use them inline without clutter. ds char is a low-level accessor. It gives you the character at a position and gracefully returns a null character if you're out of bounds. It's small but important when writing parsers or scanners. One of the more interesting helpers is ds iterate lines. Instead of returning a list or splitting the string, which would mean allocating lots of new memory, this function takes a callback. It walks through each line and calls your function with a pointer and length. That keeps iteration 0 copy and efficient, and you can stop early just by returning false from your callback. Finally, there's ds ensure. This one underpins all the appending and insertion functions. It guarantees there's enough capacity for extra data, growing the buffer if needed, but without touching the actual string content. Exposing it as part of the API lets power users pre-grow their buffers and avoid repeated allocations during heavy use. Let's look at the conversion functions first. ds to int wraps str to int convert the string to a signed integer. I keep an int pointer so I can detect if no characters were converted at all. After parsing, I also check the result against int min and int max so we can return a range error instead of overflowing. Finally, the cast to int happens only after those checks. ds to double is the same idea, but for floating point numbers using strtod. Again, we check the enter so we can tell the caller if the string didn't contain a valid number. The next group is small utilities. ds starts with and ds ends with both compute the prefix or suffix length up front, bail out early if it's longer than the string, and then do a single strncmp to compare just that region. ds contains is even simpler. It just calls str to see if the substring exists anywhere. ds char is a safe index accessor. If you go out of bounds, it gives you a null terminator instead of reading invalid memory. ds ensure is a helper for making sure there's enough capacity before appending. It calculates the total size needed including the null terminator, doubles the capacity until it's big enough, and then does a realloc. This pattern avoids repeated small allocations and keeps the buffer contiguous. Finally, ds iterate lines is a lightweight way to process a multi-line string without copying anything. It walks through the buffer, uses memcachr to find the next new line, and calls back into your function with a pointer and a length for each line. If your callback returns false, the iteration stops early. This is an efficient, zero allocation way to scan line by line. Now that the library is fully implemented, I'll set up a simple test harness using two counters for the total tests and the past tests together with some pretty prints. In main, I initialize a bunch of din str variables that I'll reuse for different tests. After each section, I clean up with ds free to avoid leaks. At the top, I add a validate macro that wraps the actual checks. It increments the counters and calls a small helper to print passed or failed, so we get nice readable output for each test. Then I add some simple helper functions for printing test results, printing a section header, and the callback function I need for testing ds iterate lines that just increments a counter when called. Each block tests a specific feature group: initialization, append, search, transformation, and so on. Most tests are one-liners using the validate macro, for example checking that ds init sets the right magic number and capacity, or that ds clear resets length to 0. For functions that return a value, I sometimes capture it first and then check several conditions at once, like verifying ds from cstr copied the data and set the right length. File loading gets its own mini setup. I create a small test file, read it into a din str using ds from file, and then immediately remove the file to keep the workspace clean. For more complex APIs like appending formatted text or removing and inserting ranges, the tests build up a string step by step and compare the intermediate result to the expected one. This way, every piece of behavior is verified in isolation. I test the search functions on a simple fixed sentence, and the substring functions I test with every programmer's first words so I can check positions exactly. Transformation functions are equally simple and easy. And trim functions are exercised with extra whitespace. The replacement tests demonstrate the 3 replacement APIs back-to-back. Conversion tests check that parsing into integers or doubles returns correct values. Finally, the utility tests cover prefix/suffix detection, character access, and line iteration. For DS iterate lines, I use the callback I defined at the top. The DS ensure test verifies that capacity actually grows when you ask for more space. When all tests are done, the program prints a nice summary showing total, passed, and failed. If everything works, you get a green all tests passed message. That wraps up our dynamic string library. We've gone from designing and implementing each function to running a comprehensive test suite, verifying that every feature works as expected. This gives us a robust, flexible foundation for string handling in C, one that's safer and far easier to use than raw character arrays. With the tests in place, extending or refactoring the library later will be much simpler and far less risky.